Alright, so we're going to determine the limit if it exists. If it exists. Okay, so, and the problem is limit as xy goes to 0, 0 of x squared over x squared plus y squared. Okay, so what are we going to do with this? Let's see. So how are we going to even like see what happens here? So first of all, we could try just like computing the limit. But if we just plug in 0, 0, that would turn out to be a 0 over 0, which is an indeterminate value or indeterminate form, right? So that wouldn't work. So a lot of these, a lot of times, because we have to prove for a limit to exist for a multivariable function, it's a lot easier to, or well, not a lot easier, but sometimes it's better to approach it that, okay, let's see where this, if this limit does not exist. So a lot of, when you approach computing or finding limits for multivariable, it's like figuring out, okay, does this even exist, and then going from there. So a kind of easy like direction or path to go from to approach a multivariable function is using the axes. So like the x-axis or the y-axis, okay? So for example, if we wanted to try the limit of this function along the y-axis, that means that we're going to set our x value, our x, set x equal to 0. Okay, so let's see what happens. So if we do that, we get limit. So if we set x equal to 0, we have 0, comma y goes to 0, 0. And then x squared over x squared plus y squared. So if we plug in that 0 for x, then we have a 0 squared over 0 squared plus y squared, which is equal to a 0, right? So that's the limit when you're approaching this point, 0, 0, along the y-axis. So when you're coming at it from this way or from this way, straight up or straight down, okay? So there's our origin, right, on the xy plane. Okay, so that's that one. So let's see if we could find, let's see what happens if we approach it along the x-axis, so like from the left or the right. So a limit along the x-axis, I can't spell, okay, hold on, axis, there we go. So that means we would set our y equal to 0. Okay, so let's see what happens now. So then we have limit as x0 goes to 0, 0. And another way, just a side note, another way to write this, since our y stayed the same, you could just say x goes to 0, because y doesn't change, right? Anyways, then we have our x squared over x squared plus y squared. And when we plug in a 0 for the y, we get x squared over x squared plus 0 squared, which is equal to x squared over x squared, which is a 1, all right? So we see here that when we're going to the same point, but along different paths, right? The first path was going this way, and the second path of approach was from left to right on the x-axis. So since these disagree, so we're going to say since the limits disagree, that's an E and an E. Okay, disagree. The limit, the entire limit, the limit that we started with, right? So this one up here, this one does not exist. Does not exist. Okay? Can't have disagreeing limits. That's not good. Okay? All right, so now on to, let's do another example. So here again, we're going to calculate a limit. Calculate the limit as xy goes to 0, 0. Okay, so to the origin of xy squared over, let's say x squared plus y squared. Okay, so this one, I'm just going to give it out that it does exist. Okay, and here we'll actually be doing two methods. Okay, we'll be exploring a couple different ways you can try to solve for a limit of multivariables. Okay, so method one, I'll label it for you guys. So method one is actually going to be the squeeze theorem, which we've probably seen before. So squeeze theorem. So we're going to start off with the useful property that that like y squared over y squared plus an x squared is always going to be, the absolute value of this is always going to be between 0 and 1. I mean, it could equal 0 if y and x both equal 0, right? But it could also equal 1 if x equals 0 and y is just something else. And it could be anything in between, right? Because this value here, that would just equal 1, regardless of what the y is. But now that we add this x in here, then it could be, the bottom could always be larger than the top, right? So we're either going to get we're going to get some kind of fraction between 0 and 1 for this value here. Okay, so if we're starting off with this, now how do we, so this is like our useful property, number 1, useful property, and you could similarly start with, if it is more fitting for your problem, for your limit, you could also start with x squared over x squared plus y squared. That also is going to be in between 0 and 1 as well, right? So anything like that, you could always do that. Anyway, so this is our useful property that we're going to start with, and then we're going to kind of try to make it into what our function is from the problem. This is our f of x, y, right? So see here how we have everything here except for that x. We're missing this. So what we're going to do is multiply times everything through with an x, okay? So if we have 0 times x on the left, okay, and then we have an x in there, so x times y squared over x squared plus y squared. So we got what we wanted in the middle, right? And then we have an x times that 1 over there. Okay, and I did absolute value x just in case, right? Okay, so anyways, now that we're here, we have that 0 is less than or equal to our function, the absolute value of our function, so xy squared over x squared plus y squared is less than or equal to the absolute value of x. Okay, so here's where squeeze theorem comes in, right? I've been building up to this. So the middle function here is our f of xy. That's the middleman. This is our like L of x, the lower function, and this is the upper function, our u of x. Okay, so what we're going to do is take the limit as xy goes to 0, 0 of the outer ones, of L of x and u of x, and then if those agree, then that means that our f of xy, that limit has to be squeezed to the limit of the other two. Okay, so again we had 0 is less than or equal to absolute value xy squared over x squared plus y squared is less than or equal to the absolute value of x. So what I'm going to do is write limit as xy goes to 0, 0 of 0, oh, sorry, that was a that was an early 0 there. Anyways, so that's of the left function here, okay? And this is just going to equal 0 because it's a 0 already. What if we took the limit of this one? Then limit as xy goes to 0, 0 of absolute value of x is also going to be a 0, right? So that means by the squeeze theorem, abbreviate, because or since, whatever way you want to phrase it, because we have that inequality here, so 0 is less than or equal to the absolute value of xy squared over x squared plus y squared is less than or equal to absolute value of x, and since we have that, we just found those two limits, right? And since limit as xy goes to 0, 0 of 0 is equal to the limit as xy goes to 0, 0 of the absolute value of x is equal to 0, then we have that the limit as xy goes to 0, 0 of our function, which is xy squared over x squared plus y squared, is equal to 0 as well. Okay, so that was the first method. We got that the limit equals 0. So that was the first method. And now let's go on to the second method. Okay, so this method number 2, I'll label it like that. That's going to be the method of polar coordinates. And keep in mind, I'm just offering or demonstrating these two kinds of methods that you could use, like A, starting with a useful property, or B, using polar coordinates. And a lot of evaluating these limits of multivariable functions is kind of like creativity, just kind of being resourceful, maybe that's a better word, being resourceful and like drawing on what you know and what you could use to try to figure out that limit or just prove that it exists, right? So both of these ways happen to work for this problem, but I'm not going to guarantee that for any kind of problem, just like any random one. So sometimes one method might work better than another. Anyways, so let's get started with this one. So polar coordinates. So first of all, let's rewrite our problem. So we're trying to find the limit as xy goes to 0, 0 of xy squared over x squared plus y squared. Okay, so here's our problem. Now let's review a little bit what are polar coordinates and how do you convert from rectangular to polar. So x, which is a rectangular coordinate, right? X and y and z are rectangular coordinates, and polar coordinates are our r and theta. Okay. All right. So x is equal to r cosine theta. Okay. Our y is equal to r sine theta. Therefore, our x squared plus y squared is equal to r squared. Okay. And let's see what else we have. So that's pretty much it. That's the basis of polar coordinates. Okay, so let's say we were to plug in, I don't know. Well, okay, let's plug in what is xy squared over, how are we going to rephrase, that's what we're basically doing, is rephrasing our f of xy into f of r theta, r comma theta. So that's what we want. So we have this, and the way we would rewrite this in polar coordinates is basically replacing every x that we see with an r cosine theta. So for example, the one on the top would be r cosine theta, okay? And then every y that we see would be replaced by r sine theta. So then we have an r sine theta there being squared because of the formula here, okay? And this is all over an r cosine theta being squared plus an r sine theta being squared as well. And I just replaced those in there using these two equations, but we could have also on the bottom, see how we have that x squared plus y squared, which is automatically an r squared. So I'll just replace the bottom with that. So we have an r squared, and you would just get that if you computed that all the way through. And then on the top we have we have three of these r's being multiplied, so r to the third times cosine theta times sine squared theta. Okay, so we have that, and now we can actually reduce, right? So if we cancel out two of those r's on top and bottom, we eventually get that we have an r cosine theta times sine squared theta, right? And so this is our function, basically, right? This is like a rewritten form of our function, the one that we're concerned with, right? So now let's see, how are we going to evaluate this in now that we have it in polar coordinates, okay? So now we have limit basically as when x and y go to 0, 0, that means our radius, our r, also goes to 0. So we're going to have r goes to 0 of our function, which is now, like, I'll just put the absolute value around it, okay? So r cosine theta sine squared theta. All right, so this is our function, and we want to know where is this going. So again, let's take advantage of some kind of property. It doesn't necessarily have to be the fraction one that I showed you in method 1, but let's take advantage of the property that cosine and sine both stay between, well, they're absolute values anyways, they stay in between 0 and 1, right? So here's the 0 and there's the 1. And it's not negative 1 and 1 because I'm saying absolute value, right? If I were to remove those absolute values, it would be between negative 1 and 1. But here, because we have those signs there, it's between 0 and 1. And now what we're going to do, like we did on the last one, we multiplied by an x. But here we're going to multiply by an r. Okay, so absolute value of r. So the left side's still going to stay 0. And then we have an r cosine theta, sine squared theta, and then less than or equal to the absolute value of r, okay? So here again, we're going to be using sort of like squeeze theorem, but the first one, the differentiation here was that we converted into polar coordinates first, and then now we're using squeeze theorem at this point. But anyways, okay, so let's find the limit of the outer functions. So limit as r goes to 0 of 0 is simply equal to 0, and limit as r goes to 0 of the absolute value of r is also equal to 0. So what that means is that by the squeeze theorem, so I'll rewrite this on the next slide so we have enough room to write our conclusion. So by the squeeze theorem. It's going to look similar to the other one, by the squeeze theorem. And here I'll say, yeah. So since we're saying since first, we're mixing it up here. 0 is less than or equal to r times absolute value of r times cosine theta sine squared theta is less than or equal to 1. No, sorry, r. Sorry, absolute value of r. Okay, and since the limit as r goes to 0 of 0 is equal to the limit as r goes to 0 of the other side, right? So of this one and then of this one is equal to 0, then we have that, then, well, and that, okay, yeah. And then the limit of our function, so limit as r goes to 0 of r cosine theta sine squared theta must equal 0. And this is also, this here is equivalent to limit as xy goes to 0, 0 of xy squared over x squared plus y squared. So that must also equal 0. Okay, so kind of a long path on that second one there. But again, that's just a different method of solving for a limit. Okay? Alright, so that's basically it for this video on limits and continuity in several variables. I hope that helped, and good luck on your homework.